We present a novel technique that extends mobile devices' interactive capabilities by detecting rich gestures performed around the device. Direct touch interaction is intuitive and popular. However, small touch screens and widgets limit the richness of user interaction, with fingers often occluding large parts of the displayed content. Our goal is to complement the touchscreen with in-air gestures to enrich the interaction vocabulary. For example, to support mode switches, application, and task management. We propose a random forest-based gesture recognition algorithm that runs in real time on mobile devices. We have developed a staged classification pipeline, greatly reducing the memory footprint of the classifiers and making random forest-based classification feasible on mobile devices. The technique uses only the device's built-in RGB cameras and robustly recognizes a wide range of gestures. The first classifier coarsely estimates the depth of the hand and rejects frames where the hand is either too close or too far from the device. This greatly reduces the variation in depth that the downstream pipeline has to deal with. The shape classification forest classifies the images into 6 gesture classes. In addition, one no-gesture class and a noise class are added to deal with hand segmentation, false positives, and reject non-gesture motion in front of the camera. Finally, a hand part classifier robustly detects fingertips and the wrist for a variety of hand poses. These can be used to implement more fine-grained, localized in-air gestures. Computing the ratio between the first and secondary mode of the probability distribution allows for the recognition and tracking of continuous gestures. For instance, this can be mapped to the size of a magnification lens. Our algorithm lends itself to a variety of novel mobile interactions that greatly extend the portable device's input space and capabilities. Our aim is to enable low-effort gestures that complement touch and allow users to quickly and more naturally perform complex tasks. Our algorithm can enable division of labor by manual input. Here, a person reads a book on his portable device. While performing the familiar finger scroll gestures to navigate the text, the user can adjust the level of the document zoom using a splayed hand gesture. In another scenario, we show bimanual mode switching. Here, a person is viewing a map on his device. While panning the map through touch, the user can adjust the zoom level using a simple splayed hand gesture. Similarly, the user can quickly switch the map type by simply performing a gun gesture. By using the pinch gesture, the user can also drag the map around. A fisheye lens is invoked using the in-air pinch gesture to magnify parts of the map. Gestures around the device can be used to streamline interaction with more complex user interfaces that require explicit mode changes, such as a drawing application. Here, the user draws with touch input, while a gesture invokes a brush selector. The menu selection can then be performed using touch, without requiring the user's finger to travel to a menu. Analogously, the closed pinch can invoke an in-place color picker. Finally, the user may drag an object across the canvas and use another gesture to place copies of the object onto the canvas. One final scenario is mobile gaming. Here we show our gesture recognition pipeline interfaced with a scroll-and-shoot game. Touch input is used to control the character's motion, whereas an in-air gesture is used to fire the gun. Our implementation is efficient enough to run in real time on very resource-constrained platforms. This makes our technique applicable in a wide range of mobile computing scenarios, including tablets and smartwatch devices. In our full paper, we give phone implementation details and pseudocode, and we report on evaluations performed on low-level aspects of the algorithm, as well as on its integration with typical applications.